Hello everyone, welcome to the linear elasticity course. In this video I'm going to discuss the vector and tensor differential operators. This is just to continue the topic that we started before in the previous meetings, which is about the vector and tensor calculus. So and let us start with the differential operator. The differential operator, it is commonly known as nabla or del. Basically we just give it this name as either nabla or del, and it is given this symbol, which is, it is as shown here, it is bold. Bold, it means that this should be a vector. So one of the important things that you should understand about the nabla operator, that it is a vector. It is by itself, it is a vector. As we discussed many times before, that a vector, it requires magnitude and direction to be fully defined. So the nabla itself, the differential operator itself, it is a vector. And we're going to use this operator basically to find the derivatives of vectors or tensors. And basically in the course of linear elasticity, we're going to deal and use this nabla operator or the del operator a lot for doing differentiation of the vectors and tensor fields basically. So what does it mean, a field? A field, this is like a function. And this function basically is going to be a function of the space, like x, y, and z. Like, for example, one of the things that we're going to consider through this course, we're going to have displacement field, we're going to have a strain field, stress field. So all of these are different fields. Fields, it means simply it is a function of x, y, and z. There is a specific function that describes a specific physical phenomenon. This function is known as a field. So how about if you do have a stress function or a stress field or whatever the type of this field? It would be a vector field or a tensor field, and we would like to, for some reason, we would like to apply some derivative to this field. So we have to use the nabla operator to perform the derivative, and we do have different ways of carrying out or performing derivatives to either vectors or tensors, as we are going to discuss through this video. Okay, so starting in let us focus for now on the rectangular coordinates. What does it mean, the rectangular coordinate? It means that you just gonna have, like, you do have a point, and this point is gonna be described in the space by x coordinate, y coordinate, and there should be like z coordinate. This is the conventional rectangular coordinate. The other coordinate that would be curvilinear, like in case that would have cylindrical coordinates. So we're gonna have the r, theta, and the z direction. In the spherical coordinate, we're gonna have r, theta, and phi or phi, which just two angles in addition to the radial direction. So forget about the cylindrical or the spherical coordinates for now, and just focus on the rectangular coordinate. Like, assume that we do have a space, and this space is described by x, y, and z as three coordinates. This three coordinate is going to describe the location of any point with respect to the 0, 0, 0 point, which is the origin point of this space. So for the nabla operator or the gradient operator basically, or the del operator, it is delta I, and we said that this delta is known as the unit vector. And the one which stands for like x, we can say that like this is delta x, and this is delta y in the y direction, and this is delta z in the z direction. So we're gonna have that, say that we do have delta x, the partial derivative of x with respect to of any physical quantity, of any field, of any physical quantity with respect to x1, which it should be x itself. And the partial derivative of the same field with respect to x2, which it should be like y. We can consider this is like y and this is like x, and x3 is gonna be the z direction. So we're gonna say that we in the z direction, we're gonna have, or the z component of a vector, as we mentioned, the nabla, it is a vector, so it has x component, it has y component, it has z component. So the x component, it is just the derivative symbol itself, like the partial, the delta with delta x, or d by dx. d by dx2, d by dx3, and so on. So this is like the partial derivative with respect to x1, partial derivative of something with respect to x2, partial derivative of something with respect to x3. x1, x2, x3, these are the x like x, y, and z coordinate if we are working in rectangular coordinates. So in some textbook, basically we may use x1, x2, x3, or simply we can use the x, y, z as we commonly use for the rectangular coordinates. So then we can represent this one. We agreed and we practiced through this course. There is no need even to write this sum, because if you just consider this I as a dummy index, it means that it should be repeated. So what does it mean it should be repeated? It means that if that is fine to write this delta in a more compact form. This is the expanded form of the delta, but this is the compact form of the delta. Is going to be like delta I. So this delta or nabla, to be more accurate, this is the nabla operator or the differential operator. It's going to be delta I, which is the unit vector in the I direction. And we said that this I stands for x, y, z, since we're already working in the rectangular coordinates. And times, or it is the delta I, and in the delta I, or in the I direction, you're going to have the partial derivative with respect to xi, where xi, in case that it is x1 or xx, so it's going to be the x coordinate. In case that the I is y, so it's going to be, you're just going to replace xy with just y, and the xz with just z, as I'm going to show you later in the next slide. Okay, so this is basically how we are going to represent, very quick. This is the expanded form of the differential operator in the rectangular coordinates, and this is the compact form of the same operator in the rectangular coordinates, as I mentioned. So now let us consider the different operation, the different derivatives of some fields, starting with the scalar field. And we said that before, a scalar field, it means that this is just a magnitude. It does not require a direction to be fully defined. It's just a scalar quantity, and this quantity, it is a field. So what does it mean, a field? It means that, for example, if we're going to say that Sxs, let us consider this example. If we said that S equals 5, so this is a scalar quantity, right? If we said that X equals, for example, 7, -2, any number, so this is just a scalar quantity. But how about if we do have this S, but the S is written in this form, like S, it is 2x squared y plus, for example, 7yz squared plus x z squared. So it is a function, right? It is a function of x, y, and z in the 3 space. So we're going to say in the 3 coordinates. So we're going to say that this should be a function of x, y, and z. So this is known as a field in terms of, since in many fields of study, we represent the function, because this function, it should represent a specific physical phenomenon that we're already using in our application. Here in this course, we are working on linear elasticity. So linear elasticity, there are some specific fields, there are some specific functions that we're going to use to describe the linear elastic behavior of materials through this course, like the strain, like the stresses. So all of these are fields. So this is the meaning of a field. A field is simply, it is a function of a space. Like if we are working on the rectangular coordinate, this field is just a function that describes a specific physical phenomena in the x, y, and z coordinates, as shown as like the example of the S as a function of x, y, and z as shown here. Okay, so this is the meaning of a scalar field. And if this field is a scalar field, it means that it just requires a value. There is no need to fully describe this field using magnitude and direction. We just require a value. It's just a simple function. Okay, so how about if we have a function and we would like to find the gradient of this scalar field or scalar function? So simply the gradient, this is the gradient operator. So we're gonna use the gradient operator, which is the differential operator. So we can say, we can give a name to this one. In general, the general expression or the general name of the operator, it is differential operator, which is commonly known as nabla or del. But we can use it to find the gradient of a scalar field. The gradient, it is like the derivative. What is the physical meaning of a derivative of any function, and you should know this thing from the mathematics, that the derivative of a function, basically, it should give us the rate of a change of this function as we through a space or through the independent parameter like x and y and z. Okay, so the gradient or the derivative in general, it means that we are interested in investigating how this function is going to change through x, through y, through z. This is the meaning of derivative. The same thing, the gradient of a field, like a scalar field, a vector field or a tensor field, it means it looks like you are finding the derivative of this field and how it changes over this space, how it changes from x to y to z and so on. This is very simple. What does it mean, the gradient of a field function or a field in general, right? So here we are interested to figure out the gradient of a scalar field like this S, and what should be the gradient of this S field. So to find it, basically, we express this one as a gradient of S. What is S? This is the scalar field. S, it would be in a symbol. You can use S, R, Q, whatever it is. Anyway, we are interested in the gradient, which is nabla S. Nabla S, it means that we're already interested in the gradient. We can even type this one in this form as gradient of S. It means that I'm interested to figure out how this S, which is a scalar field, is going to change over x, y, and z, right? So this is the gradient of a scalar function, so or a scalar field. So it's going to be nabla S, which it should be, and this is the expanded form of this scalar field, the gradient of the scalar field, and this is the compact form. As we agree, that is fine if you didn't try it. The sum here, and consider that I is a dummy index. So for example, I can write this one in another form, like for example, if we are interested in the nabla S, or the gradient of a scalar field, which is S, so the gradient of S, it should be in the compact form, as we practiced million times before. It is not necessary that you memorize all of this expanded expression or even the compact form. Let us do it as we usually do for the tensor analysis or the vector calculus that we practiced before in the previous meetings. So basically, the nabla itself, it should be, this is the compact form of the nabla, right? So the nabla is gonna be like delta I, the partial derivative with respect to xi. This is like you just gonna rewrite again the nabla, but in its equivalent compact form. So this is the compact form of the nabla. How about the S? It's just S. It is not a vector. It's just a scalar field, scalar quantity. It doesn't matter what it is. It's just S. Okay. So then basically you can, and as we agreed before, that is fine if we replace. You can write delta I on after the partial derivative operator itself, or you can just write it before, or you can even carry on the delta I outside the operation. It doesn't matter where is the location of the delta I, and we remember that the delta I, this is the unit vector, so this is by itself, it is a vector. So we can combine these two terms together, and we say that it is the partial derivative of S, which it should be like a function, with respect to xi, where xi, in case that I, it is x, so it should be the partial derivative of S with respect to x. In case that I is y, so it should be the partial derivative of S with respect to y. If it is z, if I it is z, so it's gonna be the partial derivative of S with respect to z, and so on. So, and just get on the delta I. So this is the compact form of the gradient of a scalar quantity. How about if you would like to write this one in the expanded form as we did it before? So you're just gonna assume that we do have delta x once, then we're gonna consider that we do have delta y, plus we're gonna have another component for the delta z. Like right now, you're just gonna use, as you can see, we do have in the same term I on I. So this index is repeated in the same term. It means that this index should be a dummy index. What does it mean, dummy index? As we discussed before, it means that we have to repeat it. You're gonna consider that I, x plus I, it should be y plus I, it should be z, and so on. So this is a dummy index. So we're gonna end up with like partial s with respect to x, it should be just x. Okay, so the x is just the x coordinate, it means, and the partial derivative of s with respect to the x and the I right now it is y. So the x, y, it means that this should be the y coordinate. I'm referring to the y coordinate. And here I'm going to have the partial s with respect to xz, where the xz, it means that I refer to the z coordinate. So the expanded form of this compact form is going to be the partial s with respect to x, delta x. This is the x component of this vector. So remember that this is going to give us a vector. If you multiply the vector times scalar gives vector, as we discussed before, and we agreed that the nabla operator itself, the differential operator itself, it is a vector quantity. So we're going to end up with three components as shown here. These three components are the three components, the x component, the y component, the z component of this vector, which is nabla s. Make sense? S here, it would be any function. So you're just going to do the derivative with respect to x once. You're going to do the derivative of the same function, but with respect to y. Then you're going to do the derivative of the same function, but with respect to z. If you end up with these derivatives, you're just going to substitute, plug them here. You're going to end up with the expanded form of the vector in the x, y, and z coordinates. Okay? So this is the meaning of the gradient of a scalar quantity. Make sense? So let us consider, so this is basically what we have to consider if you decided to deal with the gradient of the this scalar field. So let us consider this example here as an example. How about if we assume that we do have, assume that S, it is a scalar field that is given in this form, like it is 10, let me have a look to my notes, it is 10x yz negative 12 x square y plus 13 z square x. Let us assume that we do have this scalar field. Again, it is just a function, but it is a function, basically it is a function of x, function of y, function of z, of the three coordinates that we already have, or the three variables that we already have in this main variable, which is the scalar field itself. And how about if we are interested to figure out, it is required to find the grade. The grade, it means this stands for the gradient. The grade of S, it means that we are interested to figure out the gradient of S, which is a scalar quantity. Okay, so to find this thing, let us repeat what we've done before here. So we said that the nabla S, which is the gradient of a scalar quantity, it should be the nabla, the compact form, it is the partial derivative with respect to xi delta I. As I mentioned, that is fine to write delta I before or after the partial derivative term or operator itself. Times S is just a scalar quantity. Make sense? So then you can just multiply here the S and carry on the delta I outside the bracket or the parentheses. So we're going to end up with the delta by partial xi of the S itself. And remember that the S is already function of x, y, and z, right? And this should be multiplied times delta I, which delta I refers that this is a vector quantity. So if we decided to write this one in the expanded form, so we're going to end up with the partial S with respect to something here, which it should be x, because I'm interested in the x component. So that's why I here is going to be the x component plus the partial S by partial y, the delta y, plus the partial S with respect to z, the delta z. So this is the expanded form, and this was the compact form of this gradient, right? And now let us, and this is the given function. Remember that this is the given function. So if I ask you what should be the derivative, the partial derivative of the s with respect to x. So you're gonna, like you already have any like very simple mathematics, like you do have this function and you are required to find the partial derivative of this function with respect to x. So for example, if I ask you about the first term, just the something multiplied times delta x, the x component. So we are going to find the derivative of this function with respect to x. For the first term, the derivative with respect to x gives us 10yz. Agree? How about the second term is going to be the negative 24xy. How about the third term, which is 13z squared x? So it's going to be the plus of 13z squared. Remember that we did here derivative with respect to x. Then we are going to repeat again, but this time we are going to do the derivative but with respect to y. So if we did it with respect to y for the first term, we're going to end up with 10xz. How about the second term is going to be the negative 12x square. The third term is going to be 0 because there is no y's here in the third term. Okay? Once we do it, basically, we can do the same for the third component, which is the z component of this vector. Remember that nabla s gives vector. So this is the third component of this vector. For the first term with respect to z, we're going to end up with 10xy. For the second term with respect to z, we're going to end up with 0. There is no z's in the second term. For the third term, we do have 1z squared, which is going to be the 26zx. Agree? So this is going to give us the expanded form, and typically the value of the gradient of the scalar field, which is S, at any x, y, or z. So for example, if we are interested to figure out how this S, how this field changes in the space. For example, if we are interested to figure out how much is the value of the gradient of this scalar field at x, y, and z equals 2, -1, -2. At any point, we can find it. Simply substitute with the coordinates, with the x, y, and z components of this point, you're going to figure out how much is this gradient of the scalar field at this point. Make sense? And there are so many physical applications for sure that we are interested in the gradient of a scalar field to describe a specific physical phenomenon. So that's why one of the important things that you should consider in the vector and tensor calculus, how we can perform derivatives of scalar or vector quantities in general. Like the scalar fields, this is how we can do the gradient or the derivative of this scalar field using the gradient operator. Make sense? So this is the first operation here that we have to consider, but there are some properties to this operation that we have to consider basically. First of all, the properties. Here we're going to talk about the properties of the gradient of a scalar quantity. So first of all, you should understand that it is not commutative. So what does it mean? It means that, for example, if we do have nabla s, how about if we decided to just switch the positions? Like instead of having nabla s, how about if we do have s nabla? This is not equal to this one. This is not commutative, but if they do equal, we're going to say that this is a commutative operation. But this operation, basically, it is not commutative operation. It means that nabla s is not equal to s nabla times nabla. If you switch, we're going to end up with different things, right? If you try, we're going to end up with a different vector. It means that the derivative itself, it means that, for example, this term here, we are finding the gradient of s. But this term, we are finding the s times the gradient of another thing that should be multiplied here. It means that we are interested in the gradient of another field, not in the gradient of s itself. Okay, so that's why these two operations, they are not equivalent. The second property is that it is not associative. It means not associative. So what does it mean? It means that, for example, if we do have the nabla of r times s, where the r and the s, these are two different scalar fields. Both are two different scalar fields. All right? So how about if we added a bracket here, a parentheses? It means that we are interested in the gradient of r and then this gradient of r, it's going to be multiplied times another scalar value function or a scalar field, which is s, right? This operation is not equivalent in case that we did like the multiplication of the two scalar fields first, then we're going to find the gradient of the multiplication of the two scalar fields. This operation is different than this one. They are not equivalent. Okay, if you try it, you are going to find that both are equivalent. And this makes sense. For example, if I ask you, for example, if we are interested in the gradient of x squared times y in this way. So what is the gradient of x squared? You're just going to do the derivative with respect to x. So we're going to end up here with 2x, then you're going to multiply it times I. I is going to just carry on the I as it is, just is going to be multiplied. How about if we switch? How about if we do have the nabla x squared y, and we're going to do the multiplication for these two together equals. So if we did it basically, we're going to end up with two terms here. Why? Because the first term is going to be 2xy delta. This is going to be just delta x, but by the way, only one component, but here we're going to end up with two components. One component is along x, the second component is going to be in the y direction, which is going to be x squared delta y. So this is not equivalent to this one. Try it at home, you're going to find that there is difference between the two operations. So what does it mean? It means that, for example, if we do have the nabla, if we're already interested in the gradient of r plus s, where r and s both are two scalar fields, or two scalar quantities or fields, it's going to be more accurate if you just said that these are fields. That is fine to distribute the delta over r plus the delta over s. So we have two options, either to sum the r field and the s field first, and the result, we're going to find the gradient of the result of the sum of r plus s, or you can directly find, or the other option, you just can calculate the gradient of r itself and the gradient of s, then if you sum them, you're going to end up with the same result. So this operation is equivalent to this one, so that's why we said that some of the properties of the gradient of the scalar, that it is distributive. Make sense? So this is for the scalar. Again, we just introduced the differential operator and how we can find the gradient of a scalar quantity or a scalar field. A scalar field, it means just simply a function, and you're just going to do derivative of this function, but you're going to do derivative with respect to x, with respect to y, with respect to z, along the x component, y component, or the z component of a vector, because the nabla s, this gives a vector. Make sense? The next operation basically that would include the nabla or the del operator is the divergence of a vector field. So a vector field, it means that we don't have a field that is described by a function, but this function, it has a magnitude, it has a value and direction in the meanwhile. So what is a vector field? This is like any vector. So I'm just gonna type here an example of vector field. Let's say that we're gonna say that V, where V stands for vector, or any other symbol. We agreed that we just gonna use any symbol for the vector, like A, B, whatever it is, and we agreed that we're gonna use this vector in uppercase, indicate that this is a vector. Anyway, we do have a vector field named A, B, V, whatever it is. This vector field is given as 2x squared, let's say, y plus z squared delta x plus 4y squared delta y negative 7 z x squared delta z, for example. So it means that this is a vector. Why it is a vector? How did we know that this is a vector? Because it has x component, has y component, has z component, 3 components. So this is a vector quantity, 0 order tensor, as we agreed or discussed before. And it is a field. So what does it mean field? Because the x component is just not, it is not just a number, but it is a function of x, y, and z. The same thing for the y coordinate, or the y component, the z component. So these components are functions in space, and remember that we're still working on the rectangular coordinate. It means that this is a vector field. This is the meaning of a vector field. How about if we are interested in the divergence of a vector field? A divergence, this you should have an idea about the diversion theorem before or in the mathematics class, and especially if you consider in the graduate level the advanced mathematics course. Okay, so the diversion theorem, as I mentioned, this is one of the mathematical operations that we basically would need to describe some specific physical phenomena. I won't gonna go through the details of this diversion theorem and how we can use it unless we cover this one in the linear elasticity when we move to the elasticity and the continuum mechanics part. But for now, we're just interested in this divergence vector field and how we can find this diversion. The diversion basically, it is the dot product of the gradient operator or the differential operator dot product of a vector. So if we said divergence, generally it is nabla dot. If we are interested in the divergence of a vector, so we're gonna say nabla dot, then you're gonna add here the vector. If we are interested, because we do have divergence of a tensor, so we're gonna add nabla dot and the tensor. So the nabla dot itself, this is the meaning of divergence. You got my point? So the nabla dot, this is the divergence of something. So here, and you should keep in mind that there is no divergence for a scalar field. The divergence would be for a vector, would be for a tensor. I'm gonna let you know why. So for example, I can type this thing in a little bit different way, like div, which stands for the divergence of V. It means that I'm interested in the divergence of V vector. So the div V, it means that intuitively or directly is gonna be the nabla V, the nabla dot V. If you remember that we mentioned that the dot product converts, the dot product of two vectors gives a scalar quantity, right? So remember that the delta itself, as we mentioned, that the delta, it is a vector, right? And the V, it is vector, because we're already working on divergence of vectors. So the dot product of two vectors, intuitively this operation should give us scalar quantity. Or in other words, to be more accurate, it should give us scalar field. It means that the divergence of a vector gives us a scalar field. You should understand this point. So how we can, what is the expanded form and the compact form of nabla V? So let us do it. How we can do it basically as we did it. What is the compact form of the delta? It is the partial derivative with respect to xi delta I, as we mentioned above here, right? This is the compact form of the delta itself, right? The nabla. So this is for the nabla times or dot, there is dot product here of the V. So we're still working in the same term. We said that what separate one term from another term is a plus or negative sign, like you sum or add two different terms. But the dot product, the cross product, or whatever it is, we still working in the same term. Since we are working in the same term, we are not allowed to use the same index multiple times. Every index should be used only once. So we already used I, so for the compact form of V vector, it should be like Vj delta J. As you can see, I switched the J. I switched to J. I'm using a different index. Why? Because I'm still working with the same term. Then what we're gonna do, your objective is just do the multiplication. So we're gonna have here the partial by partial xi Vj. We can just collect these two terms together or these two values together, and we're just gonna work over the delta I dot delta J. Make sense? So if we're gonna carry on here for this case, so let me move this one down, this part down a little bit. All right, so I moved it down. So let us continue here, this part. So this is, so what we did here, we just have the partial by partial x Vj, and we are going to do the operation, the dot operation itself over the unit vectors. And if you remember, if you can recall that we said that delta I dot delta j, this gives delta ij, which is the canonical delta, right? And the properties of this canonical delta that it would be either 1 or 0. 1 in case that I equals j, but it should be 0 in case that I is not equal to j, right? So what does it mean? It means that simply we can carry on. Let us just move and carry on. So we're gonna have, this should be equal. So this term, we're just gonna carry on this term. So we're gonna have partial with respect to xi. We can add here vj, no problem, right? It means that you're already doing partial derivative of the vj field or the vj function with respect to xi. And this should give us delta ij, as we agree, like delta I dot delta j gives delta ij. How we can get rid of the delta ij? We can simply just use one index for both I and j. It means that I and j, according to this definition, it should be 1. So what does it mean? It means that that is fine if we can type this thing as partial with respect to I with respect to xi. And it means that I assume that I and j, they are equal, and then use just I for both of them. Or even you can write this thing as v partial vj with respect to xj. It is equivalent. This term is equivalent typically to this term, but here I'm using I index, but here I'm using a j index. Even you can use another different index. You can say, for example, like partial vk with respect to xk, no problems. All of these three terms, they are equivalent. Make sense? So this is, you're gonna say that the divergence of a vector gives this compact form. This is the compact form of the divergence of a vector. I'm not asking you to memorize that the divergence of V, it would be this one directly, but if you don't memorize this thing, you can just do it. You just gonna try expand it step by step till you're gonna end up with this form. This is the compact form of the divergence of a vector, kind of. How about the expanded form? How about if you decided to expand it in the x like x and y and z? And remember that we mentioned that the dot product of two vectors gives a scalar. So that's why there is no delta I here, or delta k, or delta j, right? There is no deltas here. It means that this is a scalar quantity. So this is a scalar quantity, or scalar field, you could say. So the expanded, what is the expanded form of this V? So it could be expanded as partial. Let us work over I, for example. So let us assume I, it is x once, then y plus z. Why we are adding these multiple terms, x and y and z? Because the I is a dummy index. I is repeated. The same thing for j. It is a dummy index. K is a dummy index. So if we assume that I is x, so it should be Vx. What is Vx? This is the x component of the vector field. This component should be the Vx. This component should be the Vy. This component should be the Vz component. So what I'm gonna do, the partial derivative, I'm gonna calculate or find the partial derivative of Vx with respect to x, because I is x, plus the partial derivative of Vy with respect to y, plus the partial derivative of z, but with respect to z. If you calculate or find these derivatives and sum them together, you're gonna end up with the divergence of this vector field. Make sense? So this is how we can, this is the proof, kind of, or this is the how we can drive this form, this compact forms of the divergence of a vector. We can directly do it as I explained above, and this is the compact form, and this is the equivalent expanded form of the divergence of a vector. And this was an example of a vector field. Make sense? Another thing that I'd like to mention here, in some cases you're gonna find some scholars, some researchers, some people like myself, for example, that we could write this term here. Let me write it down here. Like we can write, we agreed that the nabla v dot v equals this form, right? Which is like partial vi by partial xi, right? I can write this thing as vi comma I. So where this comma here, this comma will indicate a derivative. This comma refers, this is equivalent to like you saying that partial by partial something like xi. So for example, so this is a more compact form, because if you're gonna read some research articles or some research paper, you may find the author write vi comma I or vr comma r or vj comma j, whatever it is. It means, so what does it mean? This comma, it means that this is like a more compact form to the partial derivative with respect to xi or xj or xk. Make sense? So I can write this thing in another compact form in this way. So for example, if you gonna say, for example, if you find in any articles, let's say like we do have A, it is another vector of j comma j. So what does it mean? This means that this is the divergence of a vector. Why it is divergent? Because I can write this thing as the partial derivative of aj with respect to xj. You got it? The same thing. How about this is another example here, another example. How about if I do have like b, this is another vector, like I comma j. It means that this is equivalent to, like I'm saying that I'm going to do partial derivative of bi, but with respect to xj. So the comma here, instead of just typing partial derivative with respect to x, or xi or xj or whatever, you can just directly say comma j. So it means that you are going to differentiate this field with respect to xj. If you're gonna say that comma I, so you are going to differentiate this field with respect to xi and so on. So this is another way of representing the partial by partial xi or xj. Make sense? So it means that I can write this thing into here. I can write this one as vi comma I. If you decided to use the I as the common index, right? The dummy index. If you decided to use the j as a dummy index, it is also equivalent to, like you said, that vj comma j. It is also equivalent, like you said, that del vk comma k. So the comma here stands like partial derivative with respect to xi or xj or xk. Make sense? So this is another point here. I'm gonna just confine this thing in a box in this way. So let us consider an example here on the divergence. So let us consider this example. Assume that we do have if v, okay, let us consider v, it is a vector which is given in this form, like 2x squared, and we do have negative 4 y squared x, and we do have 7 zy squared as a vector. So this is the conventional form of a vector as we agreed, and this is like the x component, this is the y component, this is the z component of the same vector, and we are required to find the divergence of v. So it means that this should be equivalent to the nabla dot v, how much it is. So to find this thing, let us do it. So as usual, you are not required to memorize everything. Start doing from scratch, from the beginning. So the nabla, the compact form of the nabla is partial by partial xi delta I dot, which is the dot product of v. I should use another index because I'm still working with the same term. So vj delta j. If you did the multiplication, this is gonna give us partial by partial vj with respect to xi, right? And delta I dot delta j. As you remember that delta I dot delta j, this gives the canonical delta, which is delta ij. It means that we're gonna end up with partial by partial vj with respect to xi delta ij, Delta ij, to get rid of it, just use one index for both I and j. So it means that that is fine if we say that del partial by partial vi with respect to xi. I can write this one in a more compact form as vi comma I, as we agreed. Make sense? So then if I decided to write this one in the expanded form, so what is the expanded form of this thing? Is gonna be v. One time I is gonna be x comma x plus one time y, I is gonna be y comma y plus I is gonna be z, so it's gonna be z comma z. Comma here indicate that derivative with respect to x, derivative with respect to y, derivative with respect to z. So if I ask you, look into these three components. These are the three components. This is the Vx component. This is the Vy component. This is the Vz component of this vector, right? So what is the derivative of this component of the Vx with respect to x? The derivative of Vx with respect to x, it's gonna give us 4x. Make sense? And remember, there is no deltas here. This is a scalar quantity. Just calculate the derivative with respect to x and that's it. Plus the Vy, this is the Vy. Differentiate Vy with respect to y. The derivative of this term with respect to y, this gives us the negative. Gives us the negative of 8yx. Agree? How about the derivative of the z component, Vz, with respect to z? This is gonna give us the plus of 7y squared. So this is gonna be the divergence of this vector given here, and this is the divergence of the vector as required. As you can see, it is a scalar quantity. It is a scalar field because it is already a function that describe a specific physical phenomena. We don't care about the physical phenomena for now, but anyway, this is a scalar field. Make sense? There are some properties that we have to consider for the divergence of vectors. So the properties of the divergence of a vector. First of all, that they are not commutative, not commutative. So what does it mean? It means that if we say that the divergence of V or the nabla dot V, it is not equal to V dot nabla. They are not equal. These two operations, they are different. Also, it is not associative. So what does it mean? It means that if we do have nabla dot S, where S a scalar, times V, where V a vector, right? And how about if we do have the nabla of S dot V? It means that we're just gonna carry on the dot. It means, for example, and I do have here, I would like to have the nabla dot S times V. So I can do the multiplication of the scalar field times the vector, right? And do the nabla, the divergence for the results. How about if I decided to have the nabla or the gradient of the scalar field dot product times the vector field? This will not be equivalent. This is not equivalent. It means that if we move the operation here, it means that it is looks like you're gonna do this calculation first, then you're gonna do this calculation here first. This is not equivalent to this one. Both are not equivalent. But it is distributive. But it is distributive. What does it mean distributive? It means that if you do have, for example, the nabla dot of V vector plus W vector, where V and W, these are two vectors, we can, that is fine to distribute over the vector, even if we do have a scalar plus vector, but it doesn't make sense. There is no physical phenomena that you would have a scalar plus a vector. But anyway, let us consider that we do have two vectors and we're gonna sum them together first. And the result, we're gonna find the divergence of the resulted vector, because if you sum two vectors, you're gonna end up with another vector, right? So the resulted vector, if we are interested in the divergence of this vector, that is fine to find first the divergence over V of V plus the divergence of W and sum them together, you're gonna end up with the same operation. It means that it means that it is some of the properties, or one of the properties of the divergence of a vector, is that it is distributive. It means that is found to distribute the operation over the two vectors as given here. Make sense? So this is for the divergence of a vector. The next operation is the curl of a vector. So we cover the gradient of a scalar. There is no divergence of a scalar, because the divergence of a scalar, it's gonna give like nothing, right? There is no physical meaning for a divergence of a scalar. But we do have a gradient of a scalar. The gradient of a scalar gives a vector, right? But how about, for example, if we do have, the next we already discussed the divergence of a vector. Now we're gonna discuss the curl. This is another operation. So what is the curl? As we mentioned, that the divergence itself, the word diversion, the equivalent operation, it is nabla dot, or the dot product of nabla dot product something, like the divergence of a vector, so nabla dot vector, right? How about the curl? The curl, it is nabla cross vector. This is also another operation that we would use in some to describe some other physical phenomena. So in this case, we would require to do some nabla for a vector field. And remember that the vector field is just a function. So how about the nabla cross V? The nabla cross V, let us do it step by step as we practiced before. What is the compact form of the nabla? It is partial by partial xi delta I. Remember that the delta I, this is the unit vector cross. This is a cross product of V. What should be V? It's gonna be Vj delta J. Why I switch? Why am I choosing? Why I'm working with a different index? Because we're still working in the same term. Since we are working in the same term, you have to use a different index. So I used for this nabla I, then for this one I use J. You can use here J, then here I, M, L, any two indices, but they should be different anyway. Then you just gonna carry on the multiplication of these two terms, and then you're gonna do the operation itself, the cross product. It should be done over the unit vectors. Very simple. So simply we're gonna have here the partial by partial xi Vj. Then we're gonna do the cross operation over the delta I cross delta J. If you recall that, if you remember that we said delta I cross delta J, this should give us the I epsilon I, the permutation parameter, which is epsilon I J. Then you're gonna add another index that you didn't use before. Like we already have here ij, right? So we're gonna carry on epsilon ij, then we're gonna use k. We didn't use k before. Delta k. Make sense? This is the permutation parameter, and if you remember that this one, it would be either 1, it would be -1, it would be 0, right? Depending on what? Depending on the array or the order of these indices. In case that we do have I, then J, then K, it means that this epsilon, it should be 0. It should be 1, I'm sorry. In case that you mix up with the order, like you said, for example, J, then I, then K. So the regular order here as written there, it is I, then J, then K. It comes in this order, I, then J, then K. So if you follow this order of the indices, the value of this epsilon itself, it is 1. But if you mess up, if you have different order, like you start with J, then I, then K, or start with K, then J, then I, it means that you're already mixing the order. So it means that the value of this epsilon should be -1. It would be 0 in case that either I equals J, or I equals K, or J equals K. It means that in case that you do have any index, any two indices, if they are equal, the value of this term should be 0. This is the permutation parameter as we explained it before, right? So if we decided to carry on in this case, so the delta I cross delta j, this gives epsilon I j k delta k. So then we can write this thing like we're gonna say that we do have partial by partial xi vj, and then this term will be replaced by the epsilon I j k delta k. So as you can see, delta k, it means that we're gonna end up with a vector. Like we do have everything, all of this should be multiplied together, then we're gonna end up with a vector. And this is what we mentioned before, like the cross product of two vectors. Remember that the nabla, it is a vector, and the v itself by definition it is a vector. And if you remember that we said that the cross product of two vectors gives a vector, so that's why we're gonna end up with delta k here. That is fine if we write this term into this form. We can write this one in another form. Like if, how about if we decided to start with epsilon I j k, then we're gonna have partial by partial xi vj, no problem, still the same term, the same value. And we're gonna have here the delta k. How about if you decided for some reason, I hate the case, I decided to work with i's or j. I mean, like I want, for some reason I need this k like I, right? So it means that you are going to switch between I and the k, or you can use any other index. It means that you can play with the indices, you can change them anyway, but you should make sure of the discrepancies and the differences between these different indices. For example, if you are going to use I instead of k here, so you are not allowed to use I inside this bracket, unless here this time it should be I, but this I should be replaced by a k or any other index. You got my point? So anyway, we're gonna end up with this form of the curl of a vector. So simply, I'm not asking you to memorize this term. As of myself, I don't remember this term itself, but when I need, at any time, when I need to do curl of a vector, I just expand and move to the next step, till I end up with this form, and that's it, right? Then how about if we are required to write this one in the expanded form? This is the compact form of the curl of a vector. How about the expanded form? The expanded form, we can write this one as follows. Like we're gonna have three brackets as given here. As you can see, if I ask you what are the dummy indices, you're gonna find that the I, the j, the k, all of them are dummy indices, right? So if we just focus on the k, and let us assume first, I've something wrong here, I've messed up. So I'm gonna use here delta x, where delta x, I'm assuming k like x, plus I should have another bracket with delta y, plus another bracket of delta z, because I'm gonna add three terms over x, y, and z. Then if we decide, it means that we already have here k equals, for the first term, let us just work on the first term. So in the first term, we already have k is x. So for epsilon ij k to be 1, what should be the index I, what should be the index j? So again, I'm working with the first term. So by force, x, it should be x, because I'm working with the first term, right? So if I ask you, in case that k is x, what should be I, what should be k? So what comes after k? If we just count I, j, k, just you already rotating counterclockwise, I, j, k, and rotate in counterclockwise direction. So we said I, j, k, what comes after the k, it should be I. So the k right now is x, and what should come after the x, it should be y, then z. You got it? So if we did it basically, if we did it in this way, it means that the I, it should be y, and the j, it should be x, z. So the j should be z, so I should type here vz, and the I, it should be y in this case, right? If we did so, it means that the epsilon ijk should be 1. But how about if we mix up? It means that, how about if we switch the j, the z with the y? So epsilon ijk will be -1. How about if we have any two indices like the I and the j, they are equal, this term will be 0. So if we consider these three different scenarios, we're gonna say that for the case, just keep this one for now here. For the case that k equals x, so for the case k equals x, I'm gonna say that I do have the partial derivative of v with respect to x something here. Negative, because I'm gonna have one value as a positive one, the second value will be a -1, partial by partial something here. So we said, and remember that the v should take the j component, but the x should take the I component. So if this is x, and we said that this should be y, this should be z, so what does it mean? It means that the first term, for this term to be 1, this should be y and z. It means that we should have partial z with respect to y. Again, partial, because j it is z. So it's gonna be partial vz with respect to y. How about if we needed negative, so we have to switch. So what does it mean? It means that for k equals x, I should have I equals z, but j it should be y. So I'm gonna have the partial derivative of y with respect to z. Make sense? So simply, in this case, if you're gonna look at it, I do have the order as epsilon here. I do have ijk, then I do have j over I. So for the k, I should have here, for the k, in case that there is x, I should have here partial vy with respect to z and z with respect to y. Because we mentioned like x, y, z, then I'm going to switch. Make sense? So this is how it works for the first term. If you repeat it for the second term, we're gonna end up partial v by partial something, negative partial v by partial something with respect to x or y or z. So here we do have y. What comes after the y? It is z. And we should have next x. So we should have y, z, x. Y, z, x. Here we have to switch. So it's gonna be partial vx with respect to z. How about the second term? Partial by partial v by partial, negative partial v by partial something. Here we do have z. What comes after the z? It should be x. What comes after the x? It should be y. So it should be z, x, y, and here we are going to switch. So it's gonna be v partial vy with respect to x. The derivative or the partial derivative of vy with respect to x. Make sense? So this is the compact form, and this is the expanded form of this term. Make sense? If we decided for some reason to have more compact form, as we mentioned above before, that partial vj with respect to xi, we can write this term as vj comma I. Agree? So we can see that this is epsilon ijk vj comma I delta k. I can write this one if you decided to just use delta k. Just use delta k. What comes after the k? So it's gonna be partial v something with respect to something here, right? X something, negative partial v something with respect to x something here. So what comes after the j, the k? It should be I. Then kj, so it is kij, then you are going to switch here, ji. So this is another compact form, but if in case that you decided to get rid of the epsilon, so I decided to get rid of the permutation parameter epsilon, so you should have these two terms subtracted in this form, multiplied times delta k, and this is the expanded form of the curl of a vector. Make sense? So, for this one, let us consider this example here. Like, how about if we do have this vector v equals 2x squared delta x negative 4y squared x delta y plus 7zy squared delta z. And it is required to find the curl of V. We can write this thing as curl of V, how much it is. So the curl of V, it should be, how we can do it, let us do it simply, step by step. Start from scratch. So we are interested in the curl, which it should be nabla cross V. So the nabla, it should be partial by partial xi delta I cross the Vj delta j, which it should give us the partial Vj by partial xi, then delta I cross delta j. We're just gonna do the operation over the deltas. This is gonna give us epsilon ijk, because this term gives us epsilon ijk delta k, right? So epsilon ijk partial by partial Vj by partial xi delta k. I can write this thing as epsilon ijk Vj comma I delta k, and in case that you are interested to get rid of the epsilon, so you have to use two terms subtracted in this way. So we're gonna have here k, what comes after the k you're gonna switch. So what comes up, so we're gonna have Vj comma I negative Vi comma j, because what comes after the k, it should be I, then j, here ji switch here. So what next? How about if we are interested to write this one in the expanded form? So we're gonna have here three brackets, one term over x as the x component, another term over y, which should be the y component, and the third term over z, which it should be the z component. For the x component, it should be v negative v, right? So, and here we should have v negative v, and here we should have v negative v, okay? For the x component here, since we have x, what comes after the x? It should be y comma z, because we should use the other two indices, so x, y, z, and here we are going to switch z comma y. For this one, y, what should come after the y? It should be the z comma x, then we should have here x comma z, and then for this case, what comes after the z? It should be x, then y, then we're gonna have y comma x. Remember the comma, this is like a derivative. So simply, if we decided to do the calculations here, so if I ask you, what is this term? This term, this is Vx. This is the x component of the vector. This is the y component Vy. This is the z component, which is Vz. So simply, if we decided to do the calculations here, what is the partial derivative of Vz with respect to y? What is Vz? Is this one. The partial derivative of this one with respect to y, this is gonna give us the first term as 14 zy. Agree? You are differentiating this term with respect to y. So it's gonna be 14 zy. Negative. How about Vy with respect to z? It means that you are going to differentiate Vy with respect to z. Do you have z's here in this term? No. So what does it mean? It means that this term is going to be 0 delta x. Make sense? Plus Vx comma z. What is Vx? This is Vx. This is Vx. Comma z, it means that we are going to differentiate this term with respect to z, but there is no z's. It means that this derivative will be 0. Negative. Vz comma x. This is Vz. Do you have x's here? No, there is no x. So this term will be 0 delta y. Plus Vy comma x, this is Vy, comma x with respect to x, so it's gonna be negative 4y squared. Negative Vx comma y, do we have y's here in this term? No, for the Vx there is no y, so this term it should be 0 delta z. So if we decided to rewrite this form, so we're gonna end up with 14 zy delta x plus 0 delta y negative 4y squared delta z. This is gonna give us the vector at the curl of the vector v, where, as you remember, that we said that the cross product of two vectors, it should give us, this is vector and this is another vector, so it should give us a vector quantity. So that's why this is the vector, which is the curl of the vector v, which is a vector field as given in this example. Make sense? So this is for the curl of the operator. The next is the gradient of a vector field. So we discussed so far the gradient of a scalar. field, the divergence of a scalar field, which is nabla dot vector, the curl of a vector, which is the nabla cross v, or a vector. Now, how about if we're gonna apply directly the differential operator over a vector, like times vector, nabla times v. There is no dot, there is no x in between them. This is gonna give us a tensor. So, if you remember above, we mentioned that the divergence of a vector gives a scalar quantity, or a scalar field. The curl of a vector gives a vector. But the gradient of a vector, so we don't have divergence, we don't have curl, we don't have gradient. The gradient of a vector gives a tensor. Why tensor? Because if you remember that we mentioned once before that the multiplication, the direct multiplication of two vectors, because the nabla is a vector and the v is another vector, if you multiply two vectors together, you're going to end up with a tensor, right? So this is direct multiplication of two vectors, which is the nabla vector and the v vector itself, known as the gradient of a vector. So intuitively or directly, you should understand that the gradient of a vector gives a tensor. So this gives a tensor. And this tensor, it should be direct. And we mentioned that the direct, this is like a first order tensor, which is just 3 by 3 components, or this one has 9 independent components. Okay. So anyway, for the gradient of a vector, what should be the expanded form and the compact form of this one? So let us do it. Let us start with the compact form of the gradient, the nabla. So the nabla should be partial by partial xi delta I, right? Agree? Times directly, there is no dot here, there is no dot product, there is no x product, just time directly v, it should be vj delta j. We're gonna use another index because we're still working on the same term. Then we're just gonna do the multiplication of partial by partial xi vj. Then we're just gonna do the multiplication over delta I times delta j directly. Delta I times delta j, this indicates that this is a tensor. There is no operation, there is no specific operation to these 2 unit vectors in this form. These 2 unit vectors indicate directly that we do have a tensor. So we're gonna say that in general we do have partial vj by partial xi delta I delta j. This is gonna give us directly a tensor. How about if we decided to rewrite again this partial derivative using the comma? So we're gonna say that we do have vj comma I delta j. So again, this is a tensor. I can even assume that this term, it is like tau ij. We used to use this symbol for the tensor before, right? So you can even assume that we do have tau ij delta I delta j, and where the tau ij, it should equal to the vj comma I, like the derivative of the j component of the vector with respect to xi. Make sense? So this is gonna give us a tensor, and this tensor, it has with 9 independent components. This is a general tensor. It is not symmetrical tensor. It is not it is not symmetrical tensor or skew symmetric tensor. It's just a general tensor with 9 independent components. If you decided to write this tensor in the tensorial form in this way, so we're gonna say that we used to write like we do have tau xx, tau xy, right, and tau xz. Like this is the row x and this is the column x, y, and z. So we're gonna have here, looks like you're already typing, looks like we already have here x, y, z column, and we do have here the x row, the y row, and the z row, right? So we're gonna end up with, here we're gonna have the tau y x, and the tau y y, and the tau y z, and here we're gonna have the tau, this should be z, zx, tau zy, and the tau zz. And remember that there is a little bit shift in the indices. Like if we mention tau ij, we should have vj comma I. This is what I assumed, right? So it means that I'm gonna have here vx comma x. Here I'm gonna have vy comma x. Just observe the indices. xy, I'm using here yx because there is a shift, right? Then I'm gonna have here vz comma x, and we do have here vx comma y. Then we're gonna have here vy comma y, vz comma y. Then we're gonna have which x comma z, then vy comma z, then vz comma z. This is gonna give us the tensor. So again, the gradient of a vector gives us a tensor. Make sense? And this is the expanded form of the tensor in the tensorial form, and this is the compact form of the same tensor, whatever, using the vj comma I, and you can even assume that the vj comma I is just the components, the different components of any regular general tensor. Make sense? So let us consider an example for this case. How about if we do have this vector, which is gonna be the same vector that we considered before, like 2x squared delta x negative for y squared x delta y plus the 7 of z y squared delta z. And we are required to find the gradient, the grade of v. It means that this should be equivalent to the gradient of v, how much it is. So the gradient of v is going to give us the tensor. So how about if we are required, just find, let us make it general. Let us find the gradient of v and the transpose of the gradient of v and the transpose of the gradient of the tensor v. Okay, so to find it, basically, let us find these to solve this example. So starting with the gradient of v, what it should be, the gradient of v. So we're gonna start with the compact form of the gradient, which is partial x delta I directly vj delta j. There is no dot, there is no cross product. Then we're gonna end up with partial vj with respect to xi. Then we're gonna have delta I delta j. There is no further operation. We can simply write this one as vj comma I, which is delta I delta j. If you decided to write this tensor in the tensorial form, so it should be written in this way. Like we're gonna have here this tensor, and we should have here the x column, the y column, the z column, and here the x, and here the y, and here the z. So you have to make sure that we are going to switch. For it means that ix j is x, so we're gonna end up with vxx, the vx comma x. Then we're gonna have here vy comma x. Then we're gonna have vz comma x. Here we're gonna have vx comma y. Then vy comma y. Then z comma y. Here we're gonna have the vx comma z. Then the vy comma z. Then the vz comma z. So these are the expanded form of the compact form of the gradient of this vector. Then our objective is just to find here. You're just gonna do the calculations for the different gradients. Our objective for now is just to find these terms. The first term, for example, is vx comma x, how much it is, and then vx comma y, then vx comma z. Then we are going to repeat for the vy comma x, vy comma y, vy comma z, and the same thing for the z components. So the x derivative of the x of the vx, the x derivative of vx, which is this one, it should give us 4x, right? So this should give us 4x. How about the y derivative of the same term, which is vx, which is 2x squared? It should be 0. There is no y. The z the z derivative, the derivative with respect to the z of vx, it should be also 0 because there is no z in the vx term. How about the vy, the second term here? So the vy comma x, how much it is? The vy comma y and the vz comma, the vy comma z. The vy, this is the first three terms. The vy comma x, this is vy. This is the vy comma x. With respect to x, we're going to end up with -4. We're going to end up with negative 4y squared because we are differentiating with respect to x. How about y comma y? So it's going to be the -8yx. The y comma z, it should be 0. There is no z's in this term, so it should be, in this case, it should be 0. Make sense? How about the other three terms, which are the, let us consider them here, the vz comma x, and the vz comma y, and the vz comma z. The vz comma x, this is the vz term, which is this one. So the vz comma x, it should be 0, there is no x there. The vz comma y, it should be 14zy, and the z comma z, it should be 7y squared. Agree? Then your objective is just to fill into this tensor. So we're going to end up with the tensor after doing these calculations. So the tensor will be in this form. So the first term, which is vx comma x, it should be 4x, vy comma x, it should be -4y squared, vz comma x, it should be 0. Then how about the vx comma y? The vx comma y should be 0. The vy comma y, -8yx. And the vz comma y, the vz comma y, it is 14zy. And how about the vx comma z? Vx comma z 0. And the vy comma z is 0. And the vz comma z, it is 7y squared. Make sense? So this is for the first requirement, which is the nabla v, the gradient of the vector v. How about the transpose of this gradient? So the transpose, because the gradient of v gives a tensor, and the transpose of a tensor is just convert the column to be row, just switch the position of the columns and the rows. So simply we know that the nabla v transpose, which it should be, the nabla v, we already got it in this form. This is the form of nabla v that we got it here, right? This is the compact form. Make sense? So this compact form of the nabla v, which is vj comma I delta j. So to find the transpose of a tensor, to find the transpose of this tensor, simply you're just gonna switch the indices of the tensor, but you're just gonna keep the unit vectors as they are, delta I then delta j. Don't switch the delta I and delta j, because if you are already switching delta I and delta j, it means that you are talking about a totally different tensor. Not even the transpose, you are talking about a totally different tensor. But the transpose, we just switch over the indices of the components of the tensor, and that's it, right? So what does it mean? It means that the transpose of this one, so this is the original tensor, and we are interested in the transpose of this tensor. So the transpose, this gives us vi comma j, and just keep delta I delta j as it is. Okay, so this is gonna give us the tensor for this one, which is simply, it should be just switch the columns and the replace positions here. So for example, we're gonna have the 4x, then we're gonna have the -4y squared, then we're gonna have the 0, then we're gonna have a 0, -8yx, then we're gonna have the 14zy, then we're gonna have the 0, 0, 7y squared. Make sense? So this is the transpose of this tensor, and this is for this example. So this is for the gradient of tensor, a vector, I'm sorry. Now let us move to another operation, which is the divergence of a tensor. So we discuss again the gradient of a scalar, divergence of a vector, curl of a vector, gradient of a vector. This is and we said that the gradient of a vector gives tensor. So now we are moving to the derivatives over tensor themselves, right? And let us move to the divergence of a tensor field. The divergence of a tensor field is, so first of all, this should give us a vector, right? As we agreed, let us know exactly what will be the result. Are we gonna end up with a vector or a tensor of this operation? So this is a vector, as we agreed, right? And the tensor is just tensor, right? It is tensor. And remember that the tensor, this is like the multiplication, this is direct, this is first order tensor. It means that there is multiplication of two vectors, like we do have here two vectors, right? So the dot, basically, the dot get the dot product. So we're gonna have like the vector, dot vector, then there should be another vector, a third vector. So the first two vectors, they're gonna be converted into scalar quantity or a scalar field, because the vector, dot vector gives a scalar. So we're gonna get rid of the first two vectors because they're gonna be converted into scalar field, and we're just gonna carry on, and we're just gonna end up with only one vector. So the divergence or a vector dot product a tensor gives a vector. Okay, so let us demonstrate this point here. It means that here the divergence of a tensor gives vector. This gives a vector. Okay, so let us figure out how we can obtain this vector, and what is the form and the shape of this vector. So just do the same. Nabla should be partial per partial xi delta I, the dot product of a tensor. Let us assume the tensor like tau ij, because it is already given by tau. And remember that we have to use different indices. We're still working in the same term, so we have to use delta tau jk, for example. We already used I, so we are not allowed to use I anymore with the tensor. We have to use other two indices like jk, delta j, delta k. This is the expression of a tensor as we practiced before. So then what we're gonna do, just do the multiplication. So we're gonna have here the partial per partial xi tau jk, just carry on the multiplication of these two terms, then do the operation itself over the delta I delta j, then you're gonna have delta k at the end, right, as a vector. And we knew before that delta I dot delta j, this gives delta ij, which is the canonical delta. So we're gonna end up with partial per partial xi tau jk delta ij delta k. Agree? So how about if you decided to get rid of the delta ij? It means that you have to use the same index for both I and j. So let us assume that let us use for both of them I, for example. So I'm gonna use for partial per partial xi tau ik. I replace j with I because I decided to both for both I and j the same index. So now I can get rid of, I can remove the delta ij, and I'm still gonna end up with delta k. Here this is vector quantity. It is a vector. It has only one delta. It has only one unit vector, delta k. So this is the compact form of this tensor. How about if you decided to use a different index? Like here I'm using the k index. How about if I decided to use I instead of k? So this k, it should be I. I'm sorry, this k, it should be I. It means that this I should be you should use another index like j with the I, because you're gonna use I. And here we're gonna use j. Make sense? So it means that is fine. This is typically equivalent. This is typically equivalent to this form, which is this one, like partial tau ji by partial xj delta I. This is, both are typically the same. They are totally equivalent. How about if you decided to use the comma instead of partial by partial x? We can type this thing as tau ji comma j. Because I'm differentiating with respect to xj, so I'm differentiating, which is comma, with respect to xj, which is j. What is the thing that you are differentiating? I'm differentiating the tau ji component of the tensor field. And remember, it is a field. It means that all the components of the tensor should be functions of x and y and z, like what we did for this example. Like this is a tensor field. Its component, it is a function of y and x and y and z. Make sense? So going back here, and then we're going to have the delta I. So this is the compact form of the divergence of a tensor. How about the expanded form of this one? You can expand it. It's going to be expanded over 3 components. Why 3 components? Because we do have delta I. You're going to have 1 component over x, 1 component over y, 1 component over z. So let us write the expanded form here. So we're going to have delta x term plus, there is another term for the delta y, and there should be a third term for the delta z. Make sense? So now let us focus on the first term. The first term states that I is already x. But if I is x, j is a dummy index that it should be repeated 3 times by summation. Some x, some plus y plus z. So what does it mean? It means that we're going to have here tau I is already x. Now let us assume that j is x, so we're going to have x comma x plus I still x, because we're still working over delta I is still x, right? Now we're going to use j is y, so we're going to have y comma y plus tau z x comma z. Make sense? So the j is a dummy index, so we have to repeat over the j, and the I is already x, so we're just going to have x. How about the second term? The second term, delta y, it means that I is already y, so I is already y, so we're going to have here tau 1 time xy comma x plus, then j is going to be y, so we're going to end up with y comma y, then j is going to be z, so it's going to be zy comma z. How about the delta z? So it's going to be tau x, it should be, I it should be z, so we're going to have x comma x plus tau yz comma y plus tau z comma z. Let me just have a space here. Tau z comma z. Makes sense? So these are the expanded form of the divergence of a tensor quantity in the expanded form. Let us consider an example here, this example. How about if we do have this tensor tau is given in this form, like 2x negative 4y and 0. We do have here negative 4y and 4y squared, and there is 0 and 0, 0, and we do have 4xz. So if I ask you very quick, what is the type of this tensor? Is it symmetrical tensor or skew symmetric tensor? It is symmetric tensor. Why? All these components, like tau, this component which is tau xy is typically the same like tau yx. The same thing, all tau xz is equal to the tau zx. Tau yz, it is equal to the tau zy. And we do have this diagonal component, it would be any other value, no problem. So this indicates that for this tensor, we do have the tau ij components are equal to the tau ji component. Even if you try to find the transpose of this tensor, is going to be the same. The same is going to give you the same tensor. It means that this is a symmetrical tensor. And how about if we are interested to find, it is required here to find what? To find the divergence of tau. So the diversion of tau, it means that we are interested to find nabla.tau tensor itself, which is gonna give us a vector as we agreed before. So how we can find this vector? Let us solve this example. So starting from scratch, the nabla of tau, the nabla.tau, this is gonna give us the delta by delta, partial by partial delta, xi delta I dot the tau, which it should be tau jk. We should use different indices, delta j, delta k, right? This is gonna give us the partial tau jk by partial xi, but we're gonna have delta I dot delta j, and we at the end we're gonna have delta k. This is gonna give us delta ij as we agreed, so we're gonna end up with partial tau jk by partial xi delta ij delta k. If we decided to get rid of the delta ij, it means that we have to use the same index for both. Let us assume that we're gonna use j index for both of them, so we're gonna end up with partial jk tau jk by partial xj, because we are using for I and j the same index delta k. If you decided to use delta k, that is fine. If you would like to switch to another index like I, so we're gonna say that we do have tau ji comma j delta I. We're just using a different index as I for the delta k, no problem. Then if I ask you to expand it, what is the expanded form? So we're gonna end up with 3 terms times delta x plus 3 other terms times delta y plus 3 other terms times delta z. So the first term will be tau xx comma x plus the tau yx comma y, because the I still are x, right? And you just switch over the j one time x, one time y, one time z, plus tau zx comma z. How about the y component? We're gonna end up with tau x y comma x plus tau y comma y plus the tau z y comma z. How about the z component? You're gonna have the I as z, so it's gonna be xz comma x plus the tau yz comma y plus the tau z comma z. Make sense? Then your objective is just to find the derivative of all of these components one time with respect to x and y and z, just to find the derivative to fill into these components. So for example, let us consider the first term here. Let us use a different current. Like, what is the derivative of the tau xx? This should be the tau xx. This should be the tau xx, right? So the derivative of this term with respect to x gives 2, right? This term should be 2. How about the derivative of tau yx? What is tau yx? This term. With respect to y, this should give us negative 4. What is the derivative of negative 4? What is the derivative of tau zx? Zx, this term is already 0, so there is no derivative, so it's going to be 0. How about the derivative of tau xy comma x? Tau xy, which is this term with respect to x, it should be 0. There is no x in this term. Tau yy comma y, the derivative of tau yy with respect to y, this gives 8y. The tau zy comma z, the tau yz, which should be this term, zy, it should be this term, which is already 0, so it should be 0. Then the tau xz, which it should be this term, is already 0, so this 0. Tau yz, which is this term, is already 0, so it should be 0. And tau zz with respect to z, this gives 4x. So we're gonna end up, at the end, we're gonna end up with this vector. Remember that this is a vector quantity. So we're gonna end up that equals, at the end, the first term will be 2 negative 4. This gives negative 2 delta x, and the second term plus 8y delta y, and the third term will be plus 4x delta z. So this is the divergence of this tensor, which is gonna give us this vector. Make sense? So this is for the divergence of the tensor. Now let us move to the curl of a tensor field. I should let you know that the curl of the tensor, it is not found in the textbook. I mean, like the textbook that I'm using for this vector and tensor analysis, they didn't, or the author didn't include this operation for the tensor because it is not common, especially if we're going to talk about linear elasticity. But as we discussed before in some other more advanced theories of mechanics and elasticity, like the non-classical theories like the micromorphic mechanics and micropolar mechanics, these curl of tensors would show up in this case. Like these, even we said that we may have, instead of diadecs, we may have triadecs as second order and third order tensors in some applications. So, but anyway, I'm just gonna let you know this one very quick, how we can find the curl. It's gonna be just the same procedure that we do. We mentioned above that the curl, it should be the nabla cross. This is the curl of cross something. It is nabla curl, it is nabla cross something. If you are interested in the curl of a vector, so you're just gonna add here the vector. If it is tensor, you're just gonna add the tensor. Here we are interested in the curl of a tensor, so we're gonna have a tensor as tau equals. What is the nabla? Should be partial by partial xi delta I cross the tensor, which it should be the tau jk delta j delta k. Make sense? Then do the multiplication of the partial by partial xi of the tau jk. Then we're gonna have a multiplication over the deltas, so we're gonna have delta I cross delta j, and we're gonna carry on the delta k. If you remember that we mentioned once before that delta I, that this term, this gives epsilon I j k. We won't gonna use k because we already have k as index, so I'm gonna use m, for example. You have to use a different m. So it's gonna be the epsilon ij, the same two indices, then use a different index that you didn't use before, like m delta m. Then let us do the multiplication. So this is gonna give us at the end the partial tau jk by partial xi and epsilon ijm delta m delta k. So as you can see, these two deltas gives us a tensor. So the curl of a tensor gives another tensor. Make sense? So we're gonna end up with a tensor, which we can write this tensor. We can even start with the epsilon in the beginning. So we're gonna have epsilon ij m, and we can use the comma as delta jk comma I, because we are differentiating with respect to xi, so it's gonna be comma I. These are the components, and we're gonna have here the delta m delta k. Make sense? If you decided for some reason to get rid of the epsilon, so we have to split it over two subtracted terms, and we're gonna use the delta m delta k. So delta m delta k, it means that we're gonna carry on the k as it is, but we're just gonna switch the positions of I and j. And so we're gonna use, for example, like tau j k comma I. It means that if we just use this term as it is, this epsilon should be 1, and it should be -1 in case that we switch the position between I and j. So we're gonna have here tau I k comma j, but it will be 0 in case that I and j are repeated indices. It means that the same index, so it should be 0. So this is the other compact form, but in case that we get rid of the epsilon, then you can expand it. But to expand this tensor, it will be expanded over 9 components, right? So basically this tensor, it is not common, and we were not gonna use it in the linear elasticity part of this course, since, or basically in this course, we will not use it. We will not use this term or this curl of a tensor, because it is not included in the linear elasticity. It will be showing up in the linear elasticity anyway. Make sense? So now let us move to the Laplacian of scalar and vector fields. The Laplacian basically is the nabla dot nabla. Like this is the dot product of two nablas together, like nabla dot nabla. This gives the Laplacian, and this is also one of the operators that would be used for describing specific phenomena of different physical systems. Anyway, so the nabla dot nabla, which is the Laplacian, basically. So again, the Laplacian itself, it is nabla dot nabla. That's it, right? So if we are interested in the Laplacian of a scalar quantity, so we're gonna say that nabla dot nabla of something here, right? So the nabla dot nabla itself equals, let us see what's gonna give us. So nabla, as we agreed, this is a vector dot vector. So the dot product of two vector, we agreed before that this is gonna give us a scalar quantity. So the Laplacian basically gives us to a scalar field, which is nabla dot nabla. So this nabla, the first nabla, should be partial by partial xi delta I dot the second nabla. It's gonna be the same, but we have to use a different index, like j, for example, delta j. Why? We're still working at the same time. Make sense? So equals. Then you're just gonna do the multiplication of the two derivatives here, like delta I partial by partial xj, and this, then you're gonna do the operation itself over the delta I dot the delta j. Make sense? This term, it should give us the delta ij, which is the canonical delta, as we agreed before. So what is this what is this partial derivative? We can write this thing as the second derivative, but with respect to xi and with respect to xj. Like, for example, you are differentiating something twice. This is the second derivative of a scalar field or a vector field, once with respect to x, then with respect to j, which is y. For example, you differentiate once with respect to x and y, with respect to x and z, with respect to x and x, whatever it is, right? So this one is equivalent to this form. Then we're gonna have here delta ij. What does it mean, delta ij? To get rid of the delta ij, it means that you have to use the same index for both. So the same index for both, and let us assume that we're gonna use I and j, we're gonna use I for both of them. So what does it mean? It means that we're gonna end up with the second derivative of, with respect to xi, with respect to xi, right? J is gonna be I. So we can write this one as the second derivative of the xi square. It means that looks like you are finding the second derivative of something. Remember that nabla by itself is just operator. It is an operator that should do something to a physical quantity or a scalar or vector field, whatever it is, right? So the Laplacian by itself, it is an operator that there should be something multiplied times this Laplacian here. Make sense? And this should give us the second derivative as given here. And as shown, there is no delta. So what does it mean? It means that this thing is a scalar quantity. This is a scalar quantity as we agreed. Make sense? So this is for the Laplacian. How about if we do have or interested to figure out the Laplacian of a scalar field, like nabla dot nabla s. Like we are interested in the Laplacian of s. So this is gonna give us as we agree, just if we decided to do it from scratch. So we're gonna have here partial by partial xi delta I dot the partial by partial xj delta j. We have to use a different index, s, just times s. So this is gonna give us the partial square by partial xi partial xj for the s. I mean that this is the second derivative of the s function. It should be like a function, once with respect to xi, another time with respect to xj, and this we're gonna do the multiplication or the operation itself over the delta. So we're gonna have delta I delta j, which should give us the delta ij, right? So if we decided to do it, so we're gonna end up with the second derivative of s with respect to xi partial xj, and we're gonna have here delta ij. Delta ij means that to get rid of it, we have to use the same index. Let us use I for both of them. So we're gonna end up with the second derivative of s with respect to xi squared. It means that that is fine to type this thing as s, which is the scalar, comma ii. Comma ii, it means that we are going, if we decided to use the comma, we are going to do a double derivative of the scalar quantity, but with respect to xi. Make sense? So if I decided to write this one in an expanded form, what is the expanded form of this thing? This is gonna give us a scalar. Anyway, this is gonna give us a scalar, because the nabla dot nabla, this gives a scalar, times scalar gives a scalar field. Okay? So if we decided to write this thing in an expanded form, we can say that this is s comma xx, because I is a dummy index, plus s comma yy plus s comma zz. Why? Because the I is a dummy index, so it's gonna be 1 time x plus 1 time y plus 1 time z, and so on. So this is gonna be the compact form of the Laplacian of a scalar field, and this is the expanded form of the Laplacian of the same scalar field. Make sense? Let us consider an example here, very quick example. How about if we do have this scalar field, S equals the 10xy z plus 12 x squared y plus 13 z squared x. So to find the Laplacian nabla dot nabla, it is required to find the nabla dot nabla of s. So this is gonna give us nabla dot nabla s. As we agreed, this is gonna be, if you just start from the scratch, we're gonna end up with s comma ii, and you should understand that s comma ii is typically the same like s comma jj or s comma rr. It means that you use any index, that is fine. The expanded form of this s comma ii, for example, is going to be the s comma xx plus the s comma yy plus the s comma zz, which is going to give us a scalar field, equals how much is the second derivative of this term. So remember that you are going to find the derivative of all the function of all of the s, twice with respect to x, twice with respect to y, plus twice with respect to z. Make sense? So how about the second derivative of all the terms? The second derivative of all the terms with respect to x. So there is no second derivative for this term, it's going to be 0. The second derivative with respect to x of this term is going to give us 2 times 1, so it's going to be 24y. Plus the second derivative with respect to x of this term is 0. So this is the second derivative of all the s with respect to x. The second derivative of all the s with respect to y. This term will be 0, there is no y squared here, there is no second derivative with respect to y to this term. The same thing here, the second derivative with respect to y of this term will be 0, the second derivative here will be 0, there is no y, so we're going to have plus 0. Plus the second derivative with respect to z. There is only one z power 1 here, so there is no second derivative of this term with respect to z. There is no second derivative here with respect to z because there is no z. Here the second derivative is going to give us 26x. The second derivative of s with respect to z is going to give 26x. So it means that the nabla dot nabla s, the Laplacian of s, gives 24y plus 26x, and this is the answer for this example. Make sense? So this is for the Laplacian of the scalar. How about the Laplacian of a vector? So let us do the same. So it's gonna be nabla dot nabla v of a vector. So nabla, the first number, nabla is going to be partial by partial xi delta I dot the second nabla, which is partial by partial xj delta j times v, which it should be vk delta k. Why I'm using a third index k? Because I'm still working in the same term, right? So we have to use with all of these three, because these are three different vectors, by the way. Okay, so we have to use with all of them different different indices, right? So let us do the calculations here. So this is gonna give us, so we're gonna multiply this time v directly. So we're gonna end up with the second derivative of vk, but with respect to xi and with respect to xj. Make sense? Then we're gonna do the operations over the deltas. So we do have delta I dot delta j. This is one operation, and the result should be multiplied times k. This should give us delta ij, as we agree, right? So delta ij, it means that we can say that we do have the second derivative of vk with respect to xi, xj, and we should have here delta ij, delta k. Make sense? All right. So this is for, you know, like this term. How about if you decided to get rid of delta I? How about if we decided to get rid of the delta I? Yes, okay. How about if we decided to get rid of the delta I? So we're gonna say that we do have here, this term is, yeah, so we have to use the same index for both I and j, right? So what I'm gonna do, let us use I, for example, for both index. So we're gonna have the second derivative of vk with respect to xi square. I'm using j as I. Now we can get rid of the delta I j, so we just carry on with the delta k. So the Laplacian of vector gives another vector. It looks like you're finding the second derivative of a vector, kind of, right? So if you decided to use k, no problem. Or if you decided to use another index, also no problem. So we can type this one, if you decided to use the comma, as vk comma ii. It means that this is the second derivative with respect to I for the vector vk, and this is going to give us another vector as delta k. Make sense? So this is the Laplacian of a vector, and we can, you know, have an example typically the same as we did before, but the only difference here that we're just going to consider a second derivative instead of just considering one single derivative of the vector, or the components of the vector itself. Make sense? So I think this is it for the differential operations over vectors, tensors, and scalar fields. Okay, and this is the objective of this video. The next video I'm gonna cover some examples. We're just gonna put some examples and we practice how we can. So we're gonna use all the things that we already covered in the vector and tensor calculus to solve this example, and this is gonna be in the next video. All right, so thank you.